All right, I want to talk about the story problem here at the end that talks about satellite radio. These are, so this type of thing, guys, is what the end of course exam in the past has shown is if they want you to solve a system, a lot of times they ask you to create the equations for that system first. Okay? So here it says, one satellite radio service charges $10 per month, plus a one-time activation fee of $20. Second service charges $11 per month, plus an activation fee of $15. So then what month will the cost of the services be the same? And then what does this point mean to us? Okay, so what we're looking for here, guys, we've got two services, and essentially you are the consumer, and you're trying to say, okay, if I'm going to have this thing for a year or 2 years or whatever, which one makes most sense in the long run? Do I pay the one that has a greater monthly access fee but a cheaper activation, or do I pay the one that has a cheaper monthly payment but a higher activation? Okay, so we have to make that decision. Which one do we want? Okay, well, when we do this, there should be a point in time where they're identical. Okay, and when we get done with this, we should be able to kind of interpret what that point is referencing for us. So let's kind of write the first equation here. Yes. In a moment, we're going to use them to solve this system. All right, so that right there gives me a statement about the first service. Tells me everything I need to know about writing an equation for the first service. Okay. We're going to let Y be the total cost of service. Okay, so when you have total cost, usually when we read these scenarios, there's going to be kind of this overall thing you're interested in. The overall thing that we're interested in is obviously the cost, right? That's usually what you let Y be. You remember Y is your dependent variable. Okay, so our cost depends on something else. Okay, what does cost depend on? Well, we're going to activate it one time. But what else is up other than the activation? Well, per month. Okay, so X is going to be the number of months. Okay, so when we write an equation here, it's going to be Y equals for service 1. Okay, what are you going to pay per month? 10 per month, right? So if I have no months, it's no dollars. 1 month is $10, 2 months 20, 3 months 30, right? Okay. But regardless of how many months I have, what does it cost to activate? $20. So if I'm looking at total cost of this thing, lost my cursor. There we go. If I'm looking at the total cost, it's going to be what I paid per month plus that initial activation fee of the original $20. So after 1 month, I paid $30. After 2 months, I paid $40. After 3 months, I paid $50, right? That kind of makes sense? Okay. Now, service 2, that's looking at that scenario. So what's that equation going to look like? Y equals 11x plus 15. Good. Okay. Now, here's the thing about this. Our y-intercepts are 15 and 20, right? And our slopes are 10 and 11. Those are pretty large values that we would have to graph on. If I gave you a piece of graph paper or I asked you just graph this on your own. So I want to use Desmos, okay? Now I sent you guys in an email yesterday, so I want you all to get in your email. I sent an applet that looks like this. And basically what it is, it's a URL that will link you to this that you can always access. And if you mess stuff up, you can always just refresh it, and it gives it back to the original graph that I've created for you, the original applet. Desmos is, obviously it's a high-powered calculator, but it allows us to do a little bit of programming. That's all I've done over here on the left-hand side, is programmed it to basically generate 2 lines in which we can drag the 2 points for those 2 lines, okay, and graph anything we want to. When you open this, okay, so it's in your email from yesterday, all this stuff on the left-hand side is the coding that I had to use You see a bunch of the formulas that maybe we're familiar with. We got a slope formula, we got some point slope formulas written in here with just some generic values. What's going on in here is the coding that allows me to move these points around as I grab them on the graph. Does that make sense? Okay. Don't mess with any of this stuff. If you mess with any of this stuff, things start to disappear, right? Does that make sense? So now I can't graph the other line. But if you do mess with that stuff, just refresh it, reload, and it gets you back to where it was. Okay. My suggestion, just hit those two arrows, get all that garbage out of there, and we've got this thing here. Okay. Now, if you've got a touchscreen is nice because you can kind of pinch and zoom and pan and all that kind of stuff to move around in there. If you don't have a touchscreen, a mouse with a scroll wheel is nice to be able to zoom in and out. Okay. If you don't have those, you've got your touchpad on your laptop. Your zoom is over here. Okay, now it's kind of predefined how each zoom is done, where you can be a little bit more precise with your touchscreen, that kind of thing. But that's a tool. Okay. Now I need to zoom out because when we look at our first graph, the first line, we had a y value, a y-intercept of 20, right? So I'm going to grab one of these red points. I'm just going to plot it on 20. Then I'm going to grab the other red point, and from 20, I'm going to apply my slope, right? So my slope was a rise of 10 and a run of 1, right? Does that make sense? So when I look at a run of 1, the way I've got zoomed in here, I should be putting that second point at 1,30. So you've got go back down to your other line. So that point right there needs to be moved. That's got to go up to 0.20. Because 20 was your y-intercept, right? If you're, and this is just the coding of things with the formulas that I generated. If your points are stacked on top of one another, your line's going to disappear. So this thing won't graph vertical lines for us. But that shouldn't be an issue for us anyways. So I get that line. That was this one here, y equals 10x plus 20. Let's do the one that y equals 11x plus 15. So I'm going to grab my blue points. One of them up to a y-intercept of 15. Okay. Then from there, I'm going to apply my slope of up 11. So it should put me at 26. And then over 1, which should put me right there. And that point, when I click on it, should be 1,26 if I've plotted these correctly. Okay? A lot of times when we do these guys, it's just because our slopes are really close together, very similar slopes. These two lines look like they're pretty much almost the same line, right? Very squeezed together. It's okay, but what's going to happen, we want to look at these things intersecting, okay? So we have to kind of scroll. And, I'm going to scroll up because if I go down here, does it look like those lines are diverging? They're getting further apart from one another? Okay. So I'm going to scroll this way and see where they cross. So it looks like they're crossing there, right? Or in this area. Does that make sense? Okay. If I just click on where I think they cross, it will find that place that they cross. And you see that little gray dot right there for me? It gives me the point 5,70. Okay? And that's an X and a Y, right? If you remember what we let X be, X was the number of months, correct? So at 5 months, these things cross. So that means that at 5 months, they're at the same price. Does that make sense? And that price is $70. Okay with everybody? What I want you to see, so which one? So the blue one, after 5 months. So if I know that I'm going to have this service for 7 months, 8 months, maybe a year or something like that, I know I'm going to have a service more than 5 months, I want to look at the line that is actually on the bottom. So this red one, what did we let that red one, that was, okay, that was the first equation, right? The y equals 10x plus 20. So after 5 months, the red line is on the bottom. So after 5 months, the red line is actually going to produce a cheaper price. Does that make sense? Okay? Until from 0 months to 5 months, the red one is on top of the blue one. Does everybody kind of visualize that? The red one is above the blue one. So if I'm only going to have this for 3 months, it makes sense to go with the red option. Okay, the, what was it, 10x plus 20. If I know I'm going to have it more than 5 months, the blue one is going to be more pricey, and the red one is the option to go with. Does that make sense? So again, the red one before 5 months is pricier. Okay, and you can do a quick comparison. If I have it for no month, isn't the red one $20 and the blue one $15? If I have it for 1 month, okay, we're looking at, so this was the 1 month here. The red one is $30 and the blue one is $26. It's not until 5 months that they're identical, and then after 5 months, they kind of flip-flop, and then the red one will be cheaper after 5 months. Okay. Not only is it important that we're able to, obviously, from the scenario, pull out the equations, which it sounds to me like we're getting pretty good at writing those equations from the words, graph them. That's really not much of the math. The math, because that's more arithmetic, that's more calculation type stuff. The math is actually interpreting what the graph is telling us, interpreting what the ordered pair is. Does that make sense? I think a lot of times we get into the mindset, because it's built into you. It's not any of your fault, but when we go through first grade, second grade, third grade, fourth grade, we think that 2 + 2 = 4 is math. We think that 3 × 7 is 21 is math, right? It's a very small component of math. It's the calculation component. It's the arithmetic component. But the math is what allows me to say 3 × 7 is 21. And then it's essentially 3 + 3 + 3 + 3 + 3 + 3 + 3, right? That multiplication is repetitive addition. So these are the ideas. When we interpret something, we understand what that ordered pair means to us. I want to make sure that we understand that is the math part. Okay. As I said yesterday, so a lot of times, unless it's a story problem, so story problems usually generate some weird numbers, like those last coefficients and y values or y-intercepts. If I was to look at this equation here, that's going to be a lot easier to use that Desmos tool that I gave you to graph those two lines and find where they intersect, okay? So please use that. Let's use that on tests and quizzes. I think it's beneficial to you to be able to do that. And my hope is that we realize that it is the same thing as if I asked you to graph it by hand on a piece of paper, right? On a piece of paper, you're going to go make a point at your y-intercept, and then from there, you're going to go up some distance and over some distance, right? Or down and over. And then it's going to plot a point, okay? And you get those two lines, this will create or 2 points, you create a line. This is just so much more precise, right? There's no human error in this as long as we put those points in the right spot and apply our slopes the right way. Yes, Travis? Are we gonna have a time? We might have a little bit of time at the end. Depends on how fast we... Huh? Yeah. If not, I can extend that last night's homework and give you a little more time so you can ask those questions tomorrow. But we're going to start 6-2. Okay, so 6-2. Or while I'm passing this out, get your homework question out, and I'll answer that before we move on to 6-2. Do you have a question, or do you just want to work on it? So what we did yesterday was ultimately developing an understanding of what the graph is doing. Okay, what these solutions mean, maybe how we can find solutions graphically. Today, we're going to find the exact same answers, but we're going to do it by algebra. Okay, instead of graphing, we're going to do it by hand. We're going to do the calculation stuff. Okay. Bruh, what?
If I'm being honest, I feel like math should be an elective.
Why?
It's the dumbest thing ever.
Why is math the dumbest thing ever?
I don't like math.
Well, that doesn't mean it's the dumbest thing ever, just because you don't like it.
Why do you need it? So when I get a job, I'm going to need how it is.
You know, I don't even know how to
Well, I mean, like, I'm not going to why. Like,
So math.
I don't like it, but I know I'm going to use it in the real world.
So math is the answer to where am I going to need this or why am I going to need this is that if you understand enough of it, for instance, some of the stuff that we're doing right now, you can use it to intelligently make decisions, right? If I've got these two services, you guys got Netflix, right? You guys sign up for Netflix. You got choices to buy it either monthly or yearly, right? Okay. If I don't know anything about math, I might just haphazardly say, oh, I'm going to buy this a subscription by month and it's going to pay me, or it's going to deduct out of my account every month. Well, if I keep that then for a year or 2 years, I've actually paid more money doing that than I would have if I would have just signed up initially for 1 year, right? That makes sense? So in regards to saving myself money and making decisions about purchases, it makes sense to learn a little bit of math so that we can make decisions. That's what, people that are in business, okay, they make decisions of, P&G. They don't just go out and say, we're going to just make as many Tide Pods as we possibly can. Because what's going to happen? Are they going to be able to sell all those? No. So they use math to kind of decide how many they should make because they know by previous experiences how many they can sell in a month or how many they can sell in a quarter or something like that. Okay. If they make too many, they have to store those, right? And if they have to store those, they have to build a building to store them, and they have to pay a mortgage on that building to store them, and they have to pay like security guards to monitor that building, right? And they have to put heat in that building and that kind of stuff. So if they make bad decisions about how many things to make, the cost of that could be exponential to them. Okay, so if they can sit down and do some of this math, and it's seriously like 9th grade math that they do, they can make a decision on how many of those Tide Pods to make and that kind of stuff. Okay, now they use 9th grade, but they also use some advanced calculus to also make those decisions as well. But that's where math is. Okay, so anybody work at like a fast food restaurant? Okay, so like if I work at McDonald's has they have analysis groups that come and watch. They'll just sit with like a tablet outside the drive-through. Okay, and a drive-through is called. You guys know what a queue is? It's called a Q-U-E-U-E. I think I just spelled weird, but it's essentially a line. Okay, so whenever you call somebody like if you ever call like a technical support, and they say you're third in line, right? There's 3 people in front of you, there's 2 people in front, you're in a queue, okay? So when you go get to the drive-thru, you're in a queue. McDonald's will send people out from their corporate office to just sit and watch queues, okay? And they'll collect data on it because they want to make sure that you, as a consumer, get fast food, right? So do they want you sitting in line at McDonald's for 25 minutes?
No, but they do.
No, okay? McDonald's, you usually don't sit there for 25 minutes, right? Okay. If you go to Happy Days, you might. Okay. Right. But like, so these like nationwide or global corporations like McDonald's, they want to make sure that you get your food in a reasonable time. Because if you get your food in a reasonable time, what are you going to probably do? You're going to come back. Okay. But if I wait, I like Happy Days food, but if I wait for 35 minutes for it, I don't really like it that much, right? So I'm probably not going to go back. If I can go to McDonald's to get my food in 5 minutes, I'm going to go to McDonald's. But think about what McDonald's doesn't want. They don't want you to pull up, order, and get your food within 30 seconds, okay? Because if you're getting your food within 30 seconds, they've got too many people working inside, okay? Does that make sense? Because they know the average customer is okay with waiting 4 or 5 minutes. So if they can maintain that wait time of like 4 or 5 minutes, then that's their kind of optimal amount of people then working on the inside. Do they want 5 people working inside and you guys getting your food real fast? No, because what do they have to do to all 5 of those people? Pay them, right? If they can have 3 people inside and you get your food within 4 minutes, is that okay? Yeah, because now you're going to be a return customer and they're paying less people. So they're making more money, right? So there's math involved, and it's high school math at its lowest foundation, a little bit of high school math, with being able to determine how to staff those places. Okay. My biggest argument is we need math, and are you going to use it in as much detail as we learn it here? Probably not. Okay. But there are instances in your life when you have to figure out something mathematical okay, to make a financial decision, and having a little bit of background with this is going to help do that, okay? Everything that you come in contact with and that you interact with on a daily basis somehow has been impacted by math. That desk, an inanimate object, there is so much math that goes into that desk that is unbelievable, okay? So imagine anything else that you come across, there's math involved in it somehow. Does that make sense?
Are we done?
No, we got to start. Well, I'm done with that. But now we got to talk about this. All right, so this is a tool. This can kind of get messy, so I'm not gonna kind of sugarcoat this and say this is one of the easier things that we do. I personally think that solving systems of equations is actually one of our harder things that we do. And the reason it's one of the harder things that we do is there's a lot of steps to it, and ultimately there's a lot of different ways you can do it. Okay, so each problem might have bare minimum 4 ways of doing it. Okay, after the next section, there might be a bare minimum like 8 ways of doing it. Okay, but that might lead to like doing it 20 different ways. So the argument is people always want in mathematics, give me the one way. Give me the one way to do this. I think that's bad. You pigeonhole yourself into one way, you might consume more time on that method than what is necessary. So I'm going to try to give you a handful of different examples here that show you multiple ways of doing something. But all at the same time, I want to show you inside one problem, I can do it 3, 4, 5 different ways, still get the same answer. Okay? But the overall governing procedure here is called substitution. We know what substitution is, right? Okay? We replace something with what it's equal to. Okay? We're going to have in our lines, in our equations, we have 2 variables, x's and y's. Okay? We're going to ultimately have a second equation that has the same x's and y's. We're going to solve one of those equations for x or solve one of those equations for y, and then substitute that or replace in your other equation that amount. Okay, and that's all substitution is. It's replacing an expression with an expression that it is equal to. Okay, if we look at those 3 bullets, I'm not going to read all these steps to you, but I want to talk about these 3 bullets in step 1, and then we'll get into some examples. These steps are here for you to go back to. You get stuck in homework, go back to, say, okay, I've done this. Okay, now I'm on step 3. What do I got to do in step 3? And you can kind of give yourself a little bit of help or guidance to get through the rest of the problem. But the goal of substitution is that when completed correctly, you're going to have, once you do the substitution, you'll have one equation left over that is going to look like an equation from chapter 2. And you just have to solve for x or solve for y. Okay? So the hope is that you have one variable left over and you're able to solve for it. Okay? Second bullet says once this is recognized, solve the resulting equation from the remaining variables. So now I'm able to take that equation that has one variable left over, and I'm able to solve it. Let's say I get x to be like 5. Okay? Now I've got x to maybe be 5 in this example. The third one says once you know that value, you're going to go back up to your original equations, and you're going to substitute that x to be 5 in, and you should be able to now solve for y in one of those original equations. Okay? So that's the idea. Substitution is going to eliminate or get rid of a variable for us. We're able to solve then for what's left over. Once we solve for what's left over, we then take that and substitute it again and solve for the other variable. Okay? These 6 steps identify how to do that. Step number 1, best thing to do, decide what variable you want to substitute. Okay? Or decide what variable you want to substitute with. Okay? And the easiest thing, and this is the idea, this is where there could be 3 to 4 different ways of doing each problem, is there's no wrong answer here. If I want to choose in my first equation, look down here. Actually, let's look at something like this. Probably like 2y plus x equals 5 and 1y minus 3x equals 12. We're going to see things like this. Okay. Step 1 says choose a variable you want to solve for. Okay. You've got 4 choices. You can solve for that y. Okay, you can solve for that x, which I think solving for that x is probably better than solving for that y, but either one is fine. Or you come down here and solve for that y, and I think that y is probably easier to solve for than either of these that we started with in the top equation. Or you can solve for that x. Does that make sense? So you've got 4 choices there that you can choose to substitute with. Okay. Step 1 there says try to identify the easiest one. Okay, and I think after we see a handful of examples, it's going to shed light on what we mean by the easiest. Okay, so each one of these questions might have, upwards of 4, 6, 8 different ways of doing them. But if there's 8 ways to complete a job, there's always a fastest way to do that job, right? Okay, so that's the hope, is that we try to find that one fastest way to do the job. Okay. What we're doing is going to be algebraically finding what we did yesterday. Where these 2 lines intersect. So if we took Desmos, okay, that I gave you a minute ago in your email. If I were to graph these 2 lines, 2x plus 3, so there's my y-intercept for 2x plus 3. Let's go up 2 and over 1. There's 2x plus 3, right? Okay. 2x plus 3. So now the other one I had was 3x minus 5, right? Let's go find minus 5. And then from there, we'll go up 3. So there's 1, 2, 3, and over 1. And those are my 2 lines, right? They intersect, right? They intersect at the point 8, 19. What we're going to do right now by hand is find that 8, 19 without the graph. Does that make sense? But from yesterday, we now know the answer to what we're going to try to work here algebraically. And as I do these problems, I'm not saying this is what you guys got to do. But if I'm taking a test, I'm taking a quiz, won't it be nice to know what the answer is before I even start working the problem? So right there, just gave you a way of doing that. Okay? Because now, instead of just kind of blindly submitting my test, I know not to go on to the next question until I figure out this one's 8, 19. Okay? So here's the idea. And this is, there's, I think I've got 3 different types here initially of the types of equations or systems of equations you might see. The first type is the easiest, but can be one of the most confusing because it's so simple. Okay? The argument is that if these 2 lines intersect, okay, the place in which they intersect, those x's are the same. Okay? So where those 2 lines intersect in Desmos was at 8, 19, right? On both those lines, the x value at 8 was the exact same position. The y value was 19. So that means to us that at that point of intersection, those 2 y values were identical. Does that make sense? Okay, so where these 2 lines cross, the x is always the same and the y is always the same. I want to look at the fact that these 2 y's are the same. Okay? Because this is what we're going to do. This is solved for y, right? This is an equation. An equation solved for y. To end up finding the ordered pair where they cross, you're going to go into your other equation. And where you see y in your other equation, which would be this right here, right? You are going to replace it with what your other equation told you y was. Doesn't this say y is 2x plus 3? Does that make sense? So you're going to rewrite this equation here on the bottom. Instead of saying y equals 3x minus 5, you're going to write 2x plus 3 equals 3x minus 5. Does that make sense? Ultimately, we're saying the same thing that these 2 said together. Isn't this, in that first equation, isn't that y? Does that make sense? Remember, when we see the equal sign means it's the word is. So y is 2x plus 3. So in that second equation, where I see y, I know I can replace it with what it's equal to. I can replace that y with 2x plus 3. When I do that, when I make that substitution, how many variables are left in that bottom equation? Do you have an x and a y down here? Don't you just have an x? Can you solve for x then? If I have 2x plus 3 equals 3x minus 5, I'm going to subtract 2x from both sides. So it gives me 3 equals x minus 5. Now what I'm going to do? Add 5. So does that end up giving me x equals 8? That make sense? Now keep in mind, when we did this graphically, wasn't the ordered pair 8, 19? And we just got the x value, right? So I know right now I've done everything correct up to this point. Okay? If I would have gotten like x to be 7 there, or 6 or something like that, I know I'm going to check my algebra again, because that's not the answer that's supposed to happen. Okay? So now we know x is 8. Now I got to figure out what the y value is. Well, aren't these rules right here? Isn't that thing a rule or a tool to tell me what y is when I know what x is? Can I plug 8 into that x right there in that top equation? Okay. Or I could plug it into that bottom one. It doesn't matter. If I want to find y, I'm going to say y equals 2 times x, which we now know x is 8, and then add 3 to it. What's 2 times 8? 16 plus 3 is 19. Just to make sure that we understand it doesn't matter, I could have gone y equals 3 times 8 minus 5. Plug it into this bottom one. What's 3 times 8? 24 minus 5? Still 19? That kind of make sense? So I just want to show you that because people always ask, well, which one do I plug it into? It doesn't matter. Okay? No, so the red one is me just checking to make sure that it doesn't matter when I plug this 8 in here. It doesn't matter whether I plug it in there or I plug it in there. Okay? But the 19 that I get, that's the y value of where these two lines cross. So the x value was 8 and the y value was 19. So what we're going to do is we're going to write an ordered pair as 8, 19, and that's our answer. And that's exactly what the graph told us we should have, right? Okay. Here's the thing. I think in this one, I'm probably only going to get 2x plus 3 equals 3x minus 5. That's probably the only equation after substituting that most people are going to get. Okay. So one way of getting this. Okay. One way of getting x to be 8. Okay. But when I solved to find 19, there were two ways to find that 19, right? So we put those things together. There's really two ways to do this problem. And that's the argument here. Let's think about this. And we're going to see this in a little bit. There might be 4 ways of doing this. 4 ways of solving for x. But once I find x, there's going to be maybe 2 ways to find y. So 4 ways and 2 ways to find y give me totally, I multiply those together, I get 8 different ways. I could have actually paired things together to solve for this ordered pair. And that's the confusion that I think most students come across, is that they want the one way. There's not one way, okay? A lot of questions there might be, like I said, 8, 10, 12 different logical ways of doing it. Does that make sense? There's always an easiest way. There's always a fastest way. But we, at the same time, should probably ask yourself, is that always the best way? So I want to do this next one. Okay, it's example 2. I think this will probably be, we'll see. We'll see where we get with this. Might be the last one. If not, we'll do one more. We got y equals 3x and x plus y equals negative 32. Okay? If you graph these, okay, y equals 3x, so I'm just going to refresh this. If y equals 3x, that means the y-intercept was 0, right? Slope is up 3 over 1. 1 would be there. Okay? The other equation was x plus y equals negative 32. X plus y equals negative 32. If I look at this, can I do this? And this is just the way I like to do it because of the ordered pairs. If x is 0, if that goes away, what's y going to be? negative 32. So that's a point that I'm going to plot. Okay? If y is 0, so that's going to go away, what's x going to be? Negative 32, right? You guys remember doing x-intercept, y-intercept technique? So 0, negative 32. It's kind of a pain in the butt to find it, but that's not the one I wanted to move. So 0, negative 32 would be that point right there, 0, negative 32. And the other one was negative 32, 0. So there. So that's using the y-intercept technique, y-intercept and x-intercepts to graph the blue line. Find their intersection, negative 8, negative 24. There's the answer that we should end up showing through the algebra. Does that make sense? Okay. So let's look at this particular problem. So which one of those equations makes the most sense to use? And the way I look at this is, when I look at that top equation, is the y variable solved for? So this one tells me exactly what y is, right? So when I go into the second one, what can I replace that y with?
No, 3x.
3x. Because this says y is 3x. So everywhere throughout the whole problem where I see y, I can replace it with 3x. Does that make sense? Okay. Now, we'll do this way, and then if we got time, I'll show you an alternative route, which it doesn't really matter if we do it that way. So we know that is going to turn into 3x. So that's going to generate then x plus 3x equals negative 32, right? How many x's you got there? Careful.
1.
Isn't this 1x and that 3x?
I thought you know how many x.
So we got 4 x's, right? Not how many do I see like written. I want to combine the like terms, right? The coefficients. So then x is going to be negative 8, right? Divide both sides by 4. Okay. Now, if I want to solve for y, I'm going to take that number of negative 8 and plug it back into one of these. So I plug it back into that one, what do I get? What's 3 times negative 8? Negative 24, right? Okay. Or, if we plug it back into this one, if I plug back into that one, it's going to be x, which was negative 8, plus y equals negative 32. What do I have to do to solve for y here? Can I add 8? Add 8. What's negative 32 plus 8? Negative 24. Okay. You don't have to do both. I think maybe doing both, substitute back into both, will confirm that you've done your work right. You get the same answer both times. But my answer now is negative 8. Negative 8 was the x. Y was negative 24. Does that make sense? Now, just kind of watch here. You don't have to write this one down. I'm going to do the same problem. But I'm going to choose to do it a different way. Would you guys agree that I could solve this equation for, let's solve it for x. Would that then, if I solve this for x, does it look like this? That make sense, everybody? All I did is I took that y and subtracted it from both sides. So I got that. Okay? Now I'm going to look at those two equations. Wherever I see an x in this equation, does it make sense to replace it now with that thing right there? That make sense? So now I'm going to rewrite all that. I'm going to rewrite this one as y equals 3, but now x is negative 32 minus y. What's this tell me to do here? Distribute. So I get y equals negative 96 minus 3y How do I solve for y now? Careful. Don't I need to get all the y's on one side? So I'm going to add 3y to both sides. And that gives me 4y equals negative 96. Anybody know how many times y goes into 96? 24 times. Okay. Was y negative 24 the first way we did this? Does that make sense? Now if I want to solve for x, can I take that negative 24 and plug it up in here and say x is equal to negative 32 minus negative 24. What's minus a negative?
You add it.
Okay, so negative 32 plus 24? Negative 8, right? Do I still get negative 8, negative 24 as my x and my y? So that's the argument. Now, I don't think anybody would hopefully, as we see more and more of these examples over the next week or so, hopefully nobody goes this route because this route was easier. This is already solved for y, so use what they're giving you. Okay? If I want to do it this way, I had to do that extra work here to solve the bottom one for x. But the argument is, does it matter? No. The idea is to solve one of your equations for a variable and then plug that into the other equation. Solve what's left over, take that answer, plug it back into one of the originals you started with, and solve that for y or x. Okay? So that's the process. That's just an introduction to this. We're going to spend a lot of time on this. I think, in my opinion, this is the hardest thing, maybe the second hardest thing that we'll do all year. Okay? There is a homework assignment. It's not due until, what's today? Tuesday, Wednesday, Thursday. It's due Thursday. Okay? Get a start on it, though, because I don't want you waiting until tomorrow night or Thursday after school to do all of these problems, because they're all going to take some time. Extend 6-1, yes. What's your question? So I'll still extend